Hello, Luke. Welcome to lesson 64. So today we're going to be talking about domain and the additive property of inequality. So let's get started. First, why don't you take out your notebook and write down this definition for domain so that that is written down and out of the way, and then we can talk about what that definition actually means. So real quickly, we'll just read it. The domain is the set of permissible values for the variables in the equation or inequality. And then there's kind of a side note here. Every equation or inequality has a domain. So why don't you write that down? Pause the video, write that down, and then unpause the video, and we'll continue in a little bit more detail. All right, so when we talk about domain and equations or inequalities, we're talking about the acceptable values that could be used in that particular equation or inequality. And sometimes the nature of the problem will actually restrict the kind of answer that we would be allowed to have. For example, if I have an inequality, let's start with that. Let's say I have x is greater than -2. Okay? And I told you to graph this. And I said, okay, let's do that. So we'll draw our line, right? And we have maybe a -3 here, maybe a -2 here, and a -1. And we just kind of write these out. 1, maybe a 2, and a 3, and so on and so forth. And if I'm going to graph this, x is greater than a -2, well, then we know that x can't be equal to a -2. X has to be greater than a -2, so we have a hollow circle. And since it's greater, it's moving off to the right for infinity, right? So anything on this blue line would be an acceptable answer to this inequality. So if I wanted to pick a point, I could pick a point, at 0. And I would say, okay, 0 is a possible solution. I could say 2 is a possible solution, or not is a possible, I shouldn't say it, it is a solution. It is a solution to this inequality. -1 is a solution. Okay, now I could also pick something a little bit more wild. I might pick something, right here, maybe. Maybe it's, 1.32164 or, 4, you get my point. Some nasty decimal. That also would be a solution to this equation, all right, or this inequality, because it is still greater than -2, and it falls on this blue line. So at any point I select on this blue line, that point is going to be a solution to this inequality, all right? But sometimes in real life, it doesn't make sense to say that, a -1 would be a solution, or maybe a 1.32164 would be a solution, okay? And that's when we have to start talking about domain, okay? So by domain, we just mean kind of that there's a pool of numbers over here, and we can select solutions, or we can select anything on this blue line, so long as it falls within this pool of numbers. And if it falls outside that pool of number, well, then we don't use it. Okay, so it has to fall inside this domain. That's what it's called. It's the domain. Okay, so it's the kind of the area in which we can select our solutions from. And anything outside of that is unacceptable. All right, so let's try to clarify this a little bit by an example. So let's say that this x is representing, the number of trees in your yard. Okay, something very simple. Let's just say that x is equal to the number of trees in your yard. Okay? Excellent. So now if x is equal to the number of trees in our yard, and then we have this inequality, x is greater than a -2, well, when you think about it, to satisfy this inequality, that everything on this blue line is an acceptable answer. But if X is the number of trees in our yard, or your yard, would it make sense to say that this point right here is a solution? It's a -1. Would it make sense to say that there are -1 trees in your yard? Absolutely not. That doesn't have any meaning to it, right? Even though it does satisfy this particular inequality, because we know what X is supposed to be, it's supposed to be the number of trees in your yard, it doesn't make sense that we would have -1 trees in our yard. Okay, so that just doesn't make sense. Another example, what about if I select this point? Well, this point is, 1.5. Well, here it's positive, so that's good. That part makes sense. But can you have 1.5 trees in your yard? I suppose if one is halfway chopped down, maybe you could call it a half a tree. But in general, we're probably going to have whole trees in our yard. Okay, so it might not make sense to say that there are 1.5 trees in our yard or your yard. Or maybe there's 1.32164 trees in your yard. Just doesn't make a whole lot of sense. So the domain for something like this, the kind of the pool of numbers that we can select answers from, is probably going to include maybe positive. Maybe we'll write it this way. This is all the positive integers. Or maybe another way to say that would be the, positive whole numbers. Okay? And if that's our domain, then I would have to say, and maybe I'll go back to my blue here, knowing that's my domain, that's going to change how I'm going to graph this. Because if X is greater than -2 and the solutions all have to fall into the positive integers, well, then I would say, okay, well, this -1 can't be a solution. And in fact, anything that's negative can't be a solution. Okay? And maybe we could say, well, 0 could be a solution. So I'll put a solid dot there. And then maybe 1's a solution. That's possible. I could have 1 tree. I could have 2 trees. I could have 3 trees. And that could go on and on forever. So bottom line, maybe I'll regraph this so that you can see clearly what would be the right answer. If I have 0, 1, 2, and 3, -1, -2, -3. Okay, so if I'm graphing this using the domain of positive integers, well then my graph is going to end up looking like this. It's going to be, 0, 1, 2, 3, and kind of, dot, dot, dot. It's going to be those those whole numbers going on for infinity. Okay? That would be my solution. Notice I didn't put any dot on the -1 because negatives don't make sense. They're not positive integers. I didn't put it on -2 for the same reason. All right? So, and I didn't put it in between these numbers. I didn't put a dot or a line between 1 and 2 because that doesn't make sense. It's supposed to be positive integers. Integers meaning whole numbers. Okay? So hopefully that makes it maybe a little bit more clear. So basically, the domain is the set of permissible values for the variables in an equation or an inequality. So it often doesn't have to do with anything mathematically. This mathematical inequality has a solution, but there's also kind of an unmathematical part to that might dictate what the domain should be, what makes sense for this particular problem. All right, so let's try another one here. So let's say I've got, let's say you're going down to the market and you're going to buy some apples. All right, and let's say you go to the market with, you have $10 with you. Okay, and let's say the price for the apples is $2 an apple. So it's, $2 per apple. Okay, and being the good math student that you are, you decide that you're going to write an equation that would show you how much a given number of apples would cost. So how would you, again, if you just pull a bunch of apples off of the cart, How would you figure out the cost for those? Well, you would take that n, we'll call the number of apples that you took off the chart or cart, we'll just call that number n, and you would multiply that number by 2 because it's $2 per apple, right? So 2 times n is going to give you the final cost. Okay? So we have a bit of an equation right here. So, let's say I decide that I'm going to buy, one apple. So if I buy one apple, well, then n is going to be equal to 1. And I'd end up with the equation 2 times 1, which is equal to 2. So it's $2, right? That's the final cost. If I wanted to buy 2 apples, I would say n is equal to 2, and I'd have to plug that in for my n, and I'd get 2 times 2 is equal to 4. So now I have $4 that I've spent. Okay? Now, what would be a suitable domain for this particular equation right here? What would be a suitable domain? All right. So think about what I'm asking with that. The domain has to do with the variable. And the variable in this case is the n, right? That's what changes depending upon what I select. If I select one apple, it's a 1. If I select 2, it's a 2. So that is my variable. So the question is, what is the domain for this variable? Or, what is kind of the pool of numbers that I can select good answers from? Okay. Maybe this pool doesn't, include all possible answers to this equation. It only includes the answers that are going to make sense for this particular situation. Okay. So what would the domain look like? Well, let's think about it. So if we're selecting apples, would, parts of an apple make sense? Could I select, 1.5, for example? And the answer to that is no. You wouldn't go into the market and select 1.5 apples. That's not the way it works. You buy whole apples. You don't buy parts of an apple. So here it's pretty clear, again, like our last problem, that the domain is going to include integers. We know that much. It's going to include, integers. Okay? Whole numbers. Now, what else could we say? Could it include negative numbers? All right, so could n possibly be a negative 1? Well, again, the answer is no. That wouldn't make sense because you can't buy negative apples. So we know it's going to be positive integers. Okay? Now, you might think that's all that you can conclude, but actually there's still something else that you could conclude here. And that is the final cost of the apples can't be greater than 10. All right? Could be less than 10, but it can't be greater than 10. So what's the maximum number of apples that would be a suitable or acceptable solution for our equation here? Well, we know that the maximum cost has to be $10. So we can plug that in. And then we know that our equation is 2 times n. So what would this n have to be in order for the final cost to be $10? Well, we can solve for n here. So we can solve by dividing both sides by 2, and we end up with n is equal to 5. So the most apples that we could buy would be 5 apples. So n could be a 1, it could be a 2, and it could go all the way up to n is equal to 5. All right? And that's at that point, that's it. We couldn't go n is equal to 6, because if we go n is equal to 6, we're not going to have enough money. It would be 2 times 6, which would be $12, and we don't have $12. So again, what we can take away from this is the pool of possible scenarios, of possible answers here, is going to include positive integers, and they have to be greater than or equal, less than or equal to 5, right? Because we cannot buy 6. All right? So that would be the domain for this problem. And hopefully that makes sense. Because again, they have to be positive, they have to be integers, and they have to be less than or equal to 5. Because those would be the values that would make sense given our scenario, our particular problem here. Okay? Even though outside of this domain, there are numbers such as, -1, or 6, or 12, or -10. We've got all these other possible answers outside of our domain that would satisfy the equation. I mean, I can certainly plug in a -1 here for an n and get a number, right? I can plug in a 12 for the n and get a number. So mathematically, these numbers outside the domain don't pose a problem. The problem lies in the fact that the problem has limitations, and it dictates to us what would be acceptable solutions. Okay? So hopefully that kind of makes sense to you. That, again, is domain. That is what domain is all about. Think of it as just, again, a pool of numbers which would be considered acceptable numbers for our particular situation. Okay? So earlier, we said that, in our notes up here, we said that every equation or inequality has a domain. And that is very true. All the equations that you've been solving up to this point, all of the inequalities that you've been graphing, they all have a domain. We just haven't talked about it. So when you think about what that domain was, well, maybe I should ask you, what would the domain be for all of the, the equations and the inequalities that we've been doing up till now? So if I gave you a problem like, 2x is equal to 10, what would be the domain for this x based, on past experience in our work, in our assignments? What has the domain for x been? All right. Was it integers? Was it negative integers, positive integers, fractions? What would be the domain for this x? Well, the answer would be the domain is all real numbers. Okay? All real numbers. So that pool of numbers that we can choose from, it was all of the real numbers. Okay? So that means this x could be negative, it could be positive, it could be a fraction, it could be pi, it could be anything that is a real number. And that's really what all of our equations and inequalities have been based on. Okay? And unless they specify what the domain is, you can assume that the domain is all real numbers. So let me say that again because that's important. When you're doing problems in the textbook, or really for the most part, any math textbook, if they don't specify what the domain is, then you can assume that the domain is all real numbers, or sometimes that's shown as this R, this fancy R we talked about before. All real numbers. All right? However, if they give you the domain, then you need to make sure that your answer is appropriate, that you've weeded out all of the other answers except for the ones that are in the domain that they state. All right, so let's try a couple problems here and kind of see how that works. So this is what you'll see in your textbook. So let's say x is greater than 3, and they want you to graph this. Let's make sure we say that. And the problem, x is greater than 3, and then they have this semicolon here, or sometimes they'll just kind of have this written off to the side. The d is equal to the set of real numbers. Okay, D stands for domain. All right, so the domain is equal to reals. In this case, there's really nothing different because like I just said a moment ago, all of our inequalities and equations, we've been assuming that the domain has been reals. We just haven't talked about it. So here, nothing would really change. To work this problem, we're just simply going to draw our number line, maybe throw in a 0, a 1, a 2, a 3, a 4, a 5 maybe. And x is greater than 3. So x cannot be equal to 3. X has to be greater than 3. So this is going to be a hollow circle. And since it's greater than 3, it's going forever in this direction. It's all real numbers. This would be all real numbers. So therefore, that's all we need to do. It's the same that we've been doing all along. Now let's look at this next one. This next one is x is less than or equal to 2, and the domain is equal to the set of integers. All right? So here we have to draw our number line. Oh, that's a terrible line. Let's get straight here. There. Okay, that's better. So here we have maybe -3, -2, -1, 0, 1, 2, 3, 4, so on and so forth. And x is less than or equal to 2. So let's first figure out where that is. 2 lives here. We know that it's less than or equal to 2. So it could be right on the 2. So it would be a solid circle. But before I do that, before I mark that solid circle, I need to ask myself, is this 2 in the domain? Yes, it satisfies the inequality, but is 2 in the domain? And the domain is integers. In other words, whole numbers. So 2 is a whole number. So 2 would be in the domain. So therefore, it's a solution. Now, normally, I would just say, okay, x is less than or... Oh, why did I put that on a 3? I'm sorry. On the 2. Should be on the 2. So normally we would say x is less than or equal to 2. So it would have to be just, a line going forever in this direction. Less than or equal to 2, and we'd be done. But however, this time, we can't do that quite yet. We have to check and make sure all of that is in the domain. Clearly it's not, because if that line that I just had is all the reals, that's all real numbers. Now I only want the integers. Okay? So 2 is an integer. It's a solution. So we're going to put our dot there. 1 would also be an integer, and it's still part of the solution. 1 is less than or equal to 2. 0 is part of the solution. -1 would be. -2 would be. -3 would be. And that's just going forever in that direction. Okay? So hopefully you see the difference here. I've drawn a bunch of dots, but I haven't drawn a solid line. And the reason being is because everything in here is off limits. We can't use any of this in here because everything in here is not an integer. Even though they do satisfy the inequality, they're not integers. So they're not acceptable answers. Okay? All right, let's move on. Let's try a couple more. So x is not greater than or equal to a -3. And the domain is the set of positive integers. Why don't you pause the video and try this one by yourself, and then we'll do it together. All right, so let's draw our number line here. And so we're talking around the -3. So maybe we'll just go, well, actually, before we do that, let's first get rid of this negated inequality. So what is this actually saying? X is not greater or equal to a -3. Well, that would mean that x would have to be less than, because it's not greater than, and it's not equal to, so we wouldn't put an equal sign here. So it's less than a -3. This is just kind of a more complicated way of saying this. So we have x is less than a -3. So let's put, maybe put some tick marks here. And we'll just call this one a 2, a 1, a 0, -1, -2, -3, -4, -5. Okay? And what are the solutions here? So x has to be less than a -3. So first we'll find where -3 lives, and that's right here. And it has to be less than a -3. So it wouldn't be equal to a -3. So normally, again, we would have just drawn our circle there and gone, okay, there, it's done. Okay? But we can't do that now, because now we have to think about the domain. And the domain is positive integers. Okay? So it has to be on this orange line, but it has to be positive integers on that orange line? And do you see any positive integers on that orange line? The answer is no. Everything is negative, and there's no way that we're going to get a positive out of that. So what's the answer here? Very simple. The answer here is the empty set. There isn't an answer. Another way to write this would be the null set. Remember this symbol for the null set and this symbol for the empty set? Both of these would be perfectly legitimate answers, and they both mean that there is no answer. Okay, there's no solution to this. There's no number that we could put into x that would satisfy this inequality and be within the domain of positive integers. Okay, so that was kind of a tricky one. Let's go on to the next one. How about this one? Again, why don't you pause the video and then do it yourself, and then we'll do it together. All right, so once again, we'll just draw some tick marks here. We'll call this the -4, -3, -2, 1, 0, 1, 2, and that should be good enough. All right, so we have x is greater than or equal to a -4. So let's find the -4, and that sits right here. Now, before I draw my solid circle on there, because it does say that x could be equal to a -4, I need to check my domain. What's my domain? Positive integers. So is this -4 a positive integer? No, it's not. So that's not going to work. Now, it is helpful, though, to think what this would be if we had a domain of all real numbers. If we had a domain of all real numbers, we would have put a solid circle here, and then we would have said x is greater than a -4, so it's going forever in this direction, all right? But what we need to do now is pull out of that just the positive integers. So we need to weed out everything else and only select the positive integers. So kind of having this black line in our heads, think about where we'd find positive integers. I'll just erase that now so it's out of the way. Positive integers would have been at the 1, at the 2, at the 3, and so on and so forth in that direction forever. Notice I did not pick the 0. Okay? 0 would be considered an integer. It is true that the 0 does belong in the integers. However, it's generally not thought of as a positive integer. It's also not thought of as a negative integer either. It's kind of neither. All right? So if they ask for positive integers, one thing to remember is that the 0 is not included in positive or negative integers. Okay? Very good. All right, moving on. Our next topic here, we have the additive property of inequalities. This one is very simple. It shouldn't take us long to get through this. All we're talking about is kind of treating inequalities as equations. Okay, so when we've learned about equations, we learned that if I have x plus 3 is equal to 4, and I want to solve for x, I can subtract 3 from both sides and get x by itself. X is equal to 1, right? I am able to subtract 3 from both sides, and it's a perfectly legitimate thing to do. We're not changing the value of x. We're not messing things up. It's totally acceptable to add a -3 to both sides. Okay? That was for equations. Well, what about for inequalities? Can you do the same thing? And the answer is yes, you can. So in that respect, inequalities are very similar to equations. You can take something and add it to one side so long as we add it to the other side. So if we want to add a -3 to this side, we can certainly add a -3 over here, and we won't change the inequality. Okay, so it works the same way as equations work. Now, I will say that not everything that we can do in equations we will be able to do in inequalities. So watch out. This is one way in which equations and inequalities are similar. But later on, you're going to see that there are some things that will change the inequality that would not change the equality, the equation. Okay? All right, so once again, though, in this case, we can subtract or add from both sides. So in this case, we'd end up with x is less than a negative 2. All right? Now that we have x is less than a negative 2, we can go ahead and graph. Okay, because notice, this would have been tricky. X plus 3 is less than 1. How would you graph that in that form? It's a little bit hard to get your mind to wrap around. Where would the x be? Where would I start? Because then I have to go up 3, and then that has to be less than a negative, or less than a 1 still. So could be a little tricky. So it's always best to first get it in the form of x is less than or equal to, or greater than or equal to, or whatever, whatever's left over, in this case a negative 2. All right. Once we get it in this form, we can actually graph. So if we graph this out, what are we going to end up with? Well, x has to be less than negative 2. So where's negative 2? We'll put negative 2 right here. It's less than negative 2. Okay. And it has to be in the reals. Well, the reals would be anything. Fractions, whole numbers, it doesn't matter. So if it's less than negative 2, we're going to have a hollow circle, and then it'll be forever to the left. Okay, that would be our solution. All right, let's try this one. So tell you what, pause the video, try this one on your own, and then we'll do it together. All right, so same thing applies. We can treat it like an equation. So we want to get x by itself, so we'll add 3 to both sides, and we end up with x is greater than or equal to a negative 1. And then we're ready to actually graph it. So we draw our line, and it's going to be greater or equal to a negative 1. So put the negative 1 there, 0 here, 1 here, 2, 3, so on and so forth. Now, before we actually draw the graph, we need to look at our domain. The domain is integers, so be careful. Fractions won't work. So x could be equal to a negative 1 based on what we have here. Is negative 1 an integer? Yes, it is. So that would be an acceptable solution. All right. Now they have to be integers, so we can't draw lines here because that would include fractions and, decimals and all of that. So we're going to go forever to the right because x is greater or equal to a negative 1, but we are only hitting the integers. Remember, 0 is an integer, but it wouldn't be considered a positive integer or a negative integer. But in this case, we don't care whether it's positive, negative. We just need an integer. So 0 is an integer. That would work. 1 would work. 2 would work, 3 would work, and obviously going on forever. Okay, so that would be our graph. Excellent. Well, I think that should pretty much cover things for today. So once again, we talked about domain, the acceptable answers for an inequality or an equation. And then we've also talked about the additive property of inequalities, which basically is just saying that for inequalities, we can use the same additive property that we used for equations. In other words, we can add or subtract things from both sides, and it won't change the inequality. All right, very good. So we will stop there for today and pick up on some more of this in future lessons.